everyone, welcome back to Fossil Friday Web Chats from the Western Science Center and the Raymond M. Alf Museum. Today we have Amber Michels from Fort Hays State University
Hi,
here.
Amber.
Hi.
Good to have you here. So I'm Brittany Stoneberg. I'm the Outreach and Communications Coordinator for the Western Science Center. And we also have Gabriel Santos here from the Raymond M. Alf Museum of Paleontology.
Hi.
He's changed since this morning, if you guys were here.
I changed for the occasion. We're going under the sea, right? So.
Right.
Incredibly appropriate costume change for today's topic. So Amber is a graduate student at Fort Hays State University. She's pursuing her master's degree in the geosciences. Her thesis topic is over trophic ecology of, I'm going to not pronounce this correctly, Amber.
Go for it.
Okay.
Actinopterygians.
That, from the Cretaceous Western Interior Seaway. As an undergraduate, she majored in geology and minored in natural history. So what did you call those things again?
Actinopterygians.
Awesome.
Ray-finned fish.
Awesome. Yes, I definitely would not have been able to pronounce that correctly at all.
No, that's okay.
Awesome.
What do they say? As long as you say it with confidence, anybody believe if the pronunciation's correct.
Exactly.
Oh yeah.
You that wasn't going to come out right no matter what I did. Awesome. Well, as always, if anybody has any questions about the talk today, feel free to throw them in the chat and we will ask them afterwards. So Amber, whenever you are ready, feel free to share your screen and we'll get started.
All right, let's start this.
Go fish.
Okay. Is it working? Okay, there we go. Maybe. Okay, there we go. All right, well, thank you so much for the introduction. Again, my name is Amber Michels, and today I'll be talking about fish food webs. So we're talking about a little bit of how we look at food webs in modern ecology versus paleontology, as well as what I've been working on as a graduate student here at Fort Hays. Okay, so we're just going to talk a little bit about me. I grew up in Minnesota, which is a land of 10,000 lakes, if you've ever heard that phrase before. It's actually a little closer to 12,000, but it's a lot of lakes. And I spent a lot of my time around water growing up. Since moving to Kansas, though, for grad school, we're pretty close to Colorado. So my boyfriend Cody, our dog Brutus, and I have been exploring a little bit more over there and a little bit more of mountain hiking, which I also really enjoy. Growing up, I've always liked going to natural history museums, science museums in general. So it's kind of cool to be able to work in that environment now as well. Well, really cool. Okay, and then additionally, some things I really enjoy are Halloween and anything that has to do with designing costumes, makeup, telling a story really. And something that's really cool about being a grad student on a campus that has a museum affiliated with it is that you get the chance to do education and outreach programs. And for example, here's a few of them. On the left is an event set up by my friend and former grad student, Kat Rivers. This is her Creatures and Crossbones event, which was aimed for adult audience. And then on the right is Pokemon Day, which was set up, organized, and everything by my friend and fellow grad student Chase Shelburne. And that one's available to the general public as well. So it's kind of cool to be able to combine all these interests and in a way where we can really tell neat and informative stories to a broad range of audiences. Okay, so I got my bachelor's degree from the University of Minnesota Duluth campus. I got that in geology. That was my major, and my minor was in natural history, which is a mix of biology and geology. And something about that area of Minnesota and a lot of Minnesota is that it has really cool, interesting geology. Like the rocks I'm standing on in that picture are some of the oldest rocks in the world. They're Precambrian in age, but that is before vertebrates. So us animals with backbones were even around. So I really didn't get a taste of working with vertebrate paleontology until I started my master's. So I'm currently working on that right now at Fort Hays State University here in Hays, Kansas. And my master's will be in geoscience with a vertebrate paleontology emphasis. So with that, today we're basically just talking about what I've been doing, boiling it down into 3 different sections of this talk. So first, we're going to start with trophic ecology, and that's basically the study of how feeding structures and feeding relationships among organisms in a community work, which basically just means we're looking at who's eating who's eating what, or being eaten by what. And we can do that a lot of different ways, and we'll talk about that today. Also, we'll be talking about the Western Interior Seaway, which is where my specimens for my research come from. It was a large seaway that cut across North America during the Cretaceous period, and we'll kind of get a look at that later too. And then finally, those actinopterygians that we were just talking about are the organisms that I'm actually studying. So they came from the Cretaceous period, and then we'll kind of explain a little bit of what we're looking at. Okay, so when people think about trophic ecology and feeding relationships, a lot of times people think about a food chain. You've probably heard that term before, talking about different animals being higher up on the food chain. So basically what that's really talking about is this type of system. So at the bottom would be things like our primary producers. So our organisms like plants, algae, cyanobacteria, organisms that are able to produce their own energy, usually through means of photosynthesis. Then you go up on the food chain and we have our primary consumers. So they're the ones eating all those little primary producers. Then secondary consumers eating them, tertiary consumers eating them, and sometimes quaternary consumers. So it's going up and up and up, bigger and bigger predators that can eat things that are lower on the food chain. So this is a good way to think about how energy goes through a system through consumption of other organisms, but it can also be really problematic because it really oversimplifies this whole process. So we really like to think of it more as a food web. So instead of a straight line chain, it's more like a lot of different interactions for these different levels of consumers and producers going on in the system. And that's great. It helps us to think about it that way, but how do we study it like that? Sometimes it can get really messy, really confusing trying to follow all the arrows. So we make something called trophic structures. So one way, and the most common way that you think about a trophic structure, are these pyramids. So at the bottom are our primary producers, and that's the biggest chunk. And then every time you go up, there's a new level. And these have decreasing energy as you go up. And basically what that means is, if you look at the figure on the right, the ones at the bottom have a lot of energy, those ones that are producing their own energy. But every time that you go up on the food chain, they only get about 10% of what they ate below them. So the energy isn't actually lost, but it's not used for energy for food consumption anymore. It's turned into things like heat. So in any sustainable community where all the organisms, all the levels have plenty of food, they're happy, they're doing well, we're going to see decreasing sizes in this pyramid as we go up. Okay, so then how do we actually study this in living or in extant organisms, which basically means modern day, still around organisms? There's a few different ways. So one way is by directly observing what they're doing. So we can actually go watch these communities, watch them eat, see who's eating them, and so on. But in marine and in fish system or communities, that can be kind of difficult to do. So a method that's used a little bit more often is gut content analysis and fecal analysis. So what ecologists do is they go out and sample a portion of the community that they think represents the community in a sample, basically. And then they take them back, dissect them, cut them open, and actually see what they've been eating. We can see in their stomach contents what they've recently consumed, in their intestines, what's already been digested, and kind of have a pretty good idea from that what their diet is. Another really cool way that ecologists can look at trophic ecology in extant animals is through DNA. So for example, this is using DNA microarrays, which basically just means they find a bunch of prey species, find a bunch of predators, and sequence their DNA. So they make these maps of all of their DNA. And then they go back out and sample a community of predators that they think represents what they're trying to look at, and then extract their DNA again and match it up to their little map and see what types of prey they've been eating. So it's really cool and really useful in small organisms like insects. Okay, and then another way that we look at trophic ecology is through the use of biomechanics. So basically, if you think of all living organisms as machines, we all have these moving parts that work together to keep us alive. And the parts that we're really interested in for trophic ecology are the ones that allow the organism to eat, to catch their prey, to process their prey. And we can look at these through mathematical and geometry to actually kind of determine what they were probably eating and how. Okay, so once they have all this information, ecologists can make trophic structures. And there's three main types that they usually make. Okay, and I'll just quickly go over them. So one is by looking at biomass in a system. So you're looking at all those different levels and you're looking at the total mass for each of those levels, which can be hard to do, but it's possible if you have a representative sample size that you can actually go out and weigh everything. Another one is by looking at the individuals in a system. So that's going out and sampling what you think is representative of the community and actually counting individually how many are at each level. And then the last one is through energy. So that one is more calculating the amount of energy provided by each of the levels in a system. And for the previous two, sometimes you can see on the right, those structures are a little bit inverted or a little bit wonky, where the lower levels aren't bigger than the ones above. And there are exceptions to where that makes sense. But I can explain that later if you have questions about that later. But
Hey, Amber, your microphone turned off.
when we're looking at ecological communities and today with modern organisms, but what do we do when we're trying to look at animals and organisms and environments that are no longer around? So let's think about that. Let's think about this list and what we can do with each of these. Okay, so we can't really observe it. We can't directly go back in time, watch these fish or these organisms hunt and be hunted and be able to make direct observations in that sense. So unfortunately, we can't really do that one. Okay, so then for DNA, a lot of times when people are thinking about prehistoric DNA or getting DNA from prehistoric animals, they flash back to that scene in Jurassic Park where there's a scientist getting DNA out of a fossil that's trapped, or of an insect trapped in fossil amber. And although amber is great for preserving skeletal structures and exoskeletons and things of that nature, it's not great for DNA, and DNA really doesn't preserve very well in the first place. Even in the best possible preservation conditions, the longest it really lasts is around 1 million years, and that's being generous. And at that point, what are we going to do with it? Because we really don't have anything to compare it to. We don't have the prey species to compare it to, and it's just not going to work for us. Okay, so the next thing is fecal analysis. So in paleontology, we call fossilized feces or fossilized poop coprolites or coprolites, and these are a couple examples. So the top one is a coprolite in, I hope you can see on my cursor, but that big bone right there is a fish vertebrae, so a backbone piece, and there's a few of them throughout this fossil. And this can be helpful as long as we can identify with the bones that are in there what type of fish it came from. We can at least tell things like about it being consumed by other predators in the system. But unfortunately, it can be difficult to do that with really small pieces, and it's really hard to tell where this poop came from, who made the poop. Usually it's not preserved at the same time as the organism, so we're kind of out of luck sometimes. But we do get lucky every once in a while. So in the bottom, you can see this fish was preserved while defecating. So it has its coprolite still with it. And if we get extra lucky, we can actually find organisms, fossilized organisms inside that coprolite and be able to match it up predator and prey. But this would be an exceptional piece of evidence that we don't often really get, unfortunately. So we're going to focus on these ones: gut content analysis, biomechanics, morphology, which basically just means how the structure of the body and what it looks like. And again, if we have a fossilization, like a site that's really well preserved, like something like a mass death assemblage that has organisms of each level, plenty of them to really be confident that it's a good representation of a community, we can do things like calculating the total biomass or the individuals or the energy in the system. But again, we usually don't get that lucky. So we're going to stick with the top two for this one. Okay, so now we're going to get into a little bit more of what I'm looking at as a grad student. So we're going to go back in time a little bit. So right now we're in the Cenozoic still, but we're going to go back to the Mesozoic. So this blue column right there. This is often referred to as the age of dinosaurs because they evolved in the Triassic and went extinct at the end of the Cretaceous. Well, except for birds, but most of what people think of for dinosaurs went extinct at the end. Okay, and then speaking of the end of the Cretaceous, we're going to zoom in a little bit, and this is actually where the Western Interior Seaway existed through North America. So it started around the end of the Albian and then went a little bit past the Maastrichtian. And my specimens actually came from a section of time in the seaway where these rocks, a big sequence of rocks called the Niobrara Formation, was deposited. And that was between 87 and 82 million years ago. So this kind of gives us an idea of what it would have looked like in North America during this time. On the left is closer to the beginning of when these rocks were being deposited, and then on the right is when they were or the end of them being deposited. So most of my specimens come from Kansas, and I highlighted that in yellow so you can kind of see it a little bit better. In the beginning, you might notice that the sea level was a lot higher, and then throughout this time period, it was a lot lower. But throughout this whole time period, throughout these millions of years, the sea level rose and fell a lot. So within this package or sequence of rocks, we have a lot of different types of rock units depending on where the sea level was at that time. Okay, so if we zoomed in and got to look inside of the seaway, it might look something like this. So being from Minnesota, I always want to be on the water, be in the water. I probably would have been tempted to go in here, but I wouldn't have wanted it to do that because this seaway was chock full of toothy predators. We had things like the mosasaurs, other marine reptiles like elasmosaurs. We had sharks, big toothy predator fish, squid-like animals with shells called ammonites. And it's just not a place you probably would have wanted to swim in. But something else about this seaway is that it was relatively warm, relatively shallow. And when you think of marine environments today, you often picture things like coral reefs or sponge beds. but this didn't have those things. So it was different than anything still around today. Instead, it had a lot more of a muddy seafloor. It doesn't really show it in this picture, but there was a lot of large, almost 6 feet in diameter clams, a lot of little oysters and things like that littering the seafloor instead. Okay, so I mentioned those big toothy fish, and that's what I'm studying for the most part. So I'm looking at the ray-finned fish. The ray-finned fish are one of 2 groups of something we call bony fish, which just basically means that they have bony skeletons all the way like us, unlike cartilaginous fish like sharks and things like that. So then within the bony fish, there are 2 groups, the actinopterygians, the ones I'm looking at with the ray fins, and the lobe-finned fish. So when the ray-finned fish, they have these really small reduced bones at their fin, and then fin rays that fan out from there. And the lobe-finned fish, their fins, if you look at it, looks a little bit more like limbs in land-dwelling animals. And that's for a good reason. We actually share a common ancestor with Sarcopterygians around today, all the way back to the early Sarcopterygii, and those are the ones that actually eventually evolved to being on land. So most of the fish that you see today are ray-finned fish, and that's what I'm studying. Okay, so you know how I mentioned with the Niobrara rocks, depending on where the sea level was, you're getting like different rocks being deposited. And one of these units of rocks was the Smoky Hill chalk, which is like this limestone that's really chalky, and it preserves fossils really well. So here's a picture of me walking through this unit and a picture with the Sternberg paleontology camps for high school students, where we actually had the opportunity to excavate, jacket, which basically just puts a plaster coating around it so that the bones don't shift around with the rock when we're trying to bring it back to the museum, and get that whole fossil out of the field. So, which was a fish. So it was really cool that we actually had that kind of opportunity to do that. Okay, so what do these fish look like? A lot of the fish were really big and predatory and toothy and just all around scary in this Western Interior Seaway. But we did have some smaller, medium to tiny fish in the seaway as well. And we even had some cool specializations. Like this fish had teeth or dentition that were specialized, we think, for crushing shells. And then we also had these really large bony fish that were filter feeders. And it's interesting because that's not something that is around today. Instead, we have things like whale sharks or whales that can actually filter feed, but we don't have these large ray-finned fish filling that role in the ecosystem anymore. Okay, so when we're looking at trophic ecology of extinct organisms, we can still do gut content analysis, but we have to be a little bit creative because we can't go in, there isn't a stomach anymore to look at. So if we get lucky enough for them to be preserved, we can actually go in and identify the type of prey that these fish have been eating. Here's an example from the Sternberg Museum. It's the fish within a fish fossil. So it's this large Xiphactinus that's preserved with also large Gilligis inside of it. So every once in a while, we do get to have that type of information. But a lot of the times we don't. So we have to use other methods. Some of those include those biomechanics I was talking about earlier, and we do this by looking at fish and organisms that are still around today that have structures and look similar to what was in the past and what's extinct. So we can kind of have a better idea and a better understanding of how they work. One of the ways I'm doing this is by looking at jaw mechanics. And I know this looks really confusing, but I'm just gonna quickly explain the basis of it. So I'm gonna use this Halloween Halloween fish decoration just to explain real quick. Okay, so basically all this is talking about is doing calculations for a ligament that pulls the jaw down during jaw opening and one that pulls it shut during jaw closing. And that basically just gives us a good idea of the amount of force and the amount of velocity that these fish could have used to actually open and close their jaws. Okay, and what that helps us to know is the type of feeding they were probably doing. So there's kind of a spectrum between ram feeding and suction feeding. And I'm just going to quickly show you some of these videos. So this is a barracuda showing us ram fighting, which is one extreme. So basically you're just going to watch him. This is super slowed down. So it's a really high speed strike, and they actually ram into their prey and bite down on it to get it. Okay, so then on the other end of the spectrum, are those using suction feeding, especially those that can actually protrude their jaws, which just means to extend it out. So if you watch this sling jaw wrasse, you can see he swims up to it, but he's not ramming into its prey. Instead, he's swimming, protruding jaw, and using suction to pull that prey specimen into its mouth. Now, most fish use a combination, especially in prehistoric fish. So it would have been a little bit more similar to this for some of them. And basically what the lower jaw ratios and jaw mechanics help us to determine is the amount of ram that they were using, likely to have been using, and the amount of suction they probably would have been using to capture their prey. Okay, so in addition to the jaw mechanics, I'm also looking at eye diameter, so the size of the eyes in comparison to the length of the fish, the size of their lower jaws in that comparison as well. And then additionally using things like the body shape, so if they're long, skinny fish, or if they're short, round fish, and what that means in modern fish, and comparing that for things like behavior or prey type and so forth. Okay, so then why is all of this important? Why do we even do studies like this when it's hard to determine what's actually going on? Well, that could be the case for any paleontological study when we can't actually go back and look at it. But really why it's so important is because understanding what's been happening in the past and what's been going on in different systems helps us to understand what we're seeing today, what is a stable system, and how long things can remain stable if they are starting to not be stable anymore, as well as give us better ideas of what we need to focus conservation efforts on versus what will probably bounce back after so long. And it really just gives us a better look at the puzzle. So if you think of every trophic study throughout different time periods, different assemblages, different organisms, it just adds one more piece to the picture that we're trying to create to understand what's been going on and how we can use this now. Okay, and that's the end for now. I can answer questions about anything that I breezed over earlier, or really any questions you have about the research I'm doing, the Western Interior Seaway, or me.
Awesome. Thank you, Amber.
Yeah, thanks, Amber. That was great.
Thanks, guys.
I really want that Halloween decoration now.
Isn't it so cool?
Cool.
Cody's sister sent it to me, and I was like, this is the most cute thing I've ever seen.
At least they didn't put ears on it like they do on all the other Halloween decorations.
Yeah, it's actually, for a piranha skeleton, it's not bad. It's simplified, but it's not bad.
I love that the jaw moves.
Yeah, right?
I was laughing on my screen when you brought that out. I was not expecting that to show up.
Well, did it help?
Yeah, actually it did. I did learn a lot more about fish than I thought. I mean, I thought I knew a little bit about fish, but I didn't know that they had those different feeding mechanics, kind of like ramming versus suction feeding. That was a really cool video too. I never seen like in slow motion, like their jaw come out that far. That was crazy.
I know, those ones are nuts. For my fish, or for my fish, but for prehistoric fish too, you don't really see that kind of protrusion until more recently. So the ability to protrude their jaws like that really has increased since the Cretaceous.
Awesome.
So, but it's crazy. Fish are crazy. They're cool.
Yeah, I wasn't super familiar with fish before this, so this was definitely very enlightening.
I'm glad.
Yeah, so again, if anybody has any questions for Amber, feel free to throw them in the chat and we will toss them her way.
Do you think that you said sponges weren't around, or like sponge um, in the Great Cretaceous, in the Seaway? So you think there would be no SpongeBob type things around there?
Yeah, I was gonna mention that earlier, but it still fits the theme. It's under the sea.
Oh man.
Oh man.
One of the things I liked is you mentioned that you used to work for the Sternberg summer camps, right? What was that like, getting to work with like kids and things like that to teach them paleo and real world paleo?
Oh, it was so cool. It was really exciting. So, like I kind of mentioned before, when I was getting my undergrad, it was very geology based. And we did do a 6-week field camp program, but it was geology, mapping, things like that. We had a small section that we got to see a couple of fossils that day. And they're like, okay, but none of you guys are really here for this, so we're going to keep going. And I was like, me. So the opportunity to actually go out in the field and not only do field paleontology, but on the things that I'm actually studying was really cool. And then having the chance to educate and talk with students that are interested in this already at the high school age was amazing. So these kids are gonna be so far ahead when the ones that really want to go into paleontology, which most of them do, they're very dedicated, they're very smart, and they were there for learning. So it's a really good group of kids. I did it for 2 years and both years were amazing. So if there's any high school and middle school students out there that want to look for programs like that, the Sternberg has a variety of different ones.
That's awesome. The Sternberg Museum is so cool. Like, since I've learned about that museum, I've just been so impressed. Right now, actually, they're doing a bunch of really great live streams on their Facebook. I know that Ian Trevathan's doing a bunch of really cool stuff. So if you're waiting between Fossil Friday chats, you can definitely check out their Facebook page to see what they're up to right now, because there's some really cool things. And I think Ian's been doing some really cool stuff with building some dinosaurs, because he's a cool prop builder. So I definitely would check those out if you've got time.
I agree. Yeah, they've had a lot of cool ones since like this whole situation started. So yeah, definitely go check them out.
Yeah, it's really cool to see how other we work for 2 smaller museums, and Sternberg is a smaller museum. It's really cool to see how regional smaller museums are really making the best of this and trying to educate our communities even while we're not able to welcome the community into our like physical building.
Right, I've been really impressed just seeing the variety of chats going out, the live streams, the activities that have been posted in education forums for people to do at home that usually you would have to go to museum and look at. So it's so cool, so innovative.
Here's a question. This is from Jim Michels. Any relation?
Yeah, I did.
He's asking, have you concluded anything unexpected from your studies?
Yes, there are. Well, right now I'm still in the process of finalizing my interpretations, but there are definitely some studies that I'm comparing to that thought that certain feeding mechanisms didn't arise until later in the geologic time period. And I'm thinking, at least currently, that it might have started a little bit sooner than we thought. So things like using or being able to eat plant material, so herbivorous fish, previously were thought to arise in the Eocene. And I think that some of my fish, or some of the, I keep calling them my fish.
Yeah, they're your fish. That's fine.
Some of these fish from the Western Interior Seaway might have been able to utilize that type of energy source.
Here's a good from our buddy Michael Ziegler, who will actually be joining us next week. He says, awesome talk. Let's see. He says, looks like the specialized feeding of these fish have increased. Are there any sorts of changes in the ecology of their environments that are changing a lot as well during this time?
Yes, there are. So some of them have to do with the coral reefs being built and coral reefs providing different types of habitat and different types of food sources for some of these animals. But something that's really driven the change is the increase in the amount of diversity of something called the spiny fish or spiny ray fish. So they're just a subset of these ray fin fish. I have a couple of them in the Western Interior Seaway collection, but as you go throughout time, these really diversify and they have to compete with each other for the same types of food sources. So specialization in how they're actually capturing this prey sometimes led to things like jaw protrusion.
Cool. We have lots of good questions coming up. This is from David, David Leverine. What's your favorite fish fossil you found in the field?
Oh, you're gonna make me answer this, aren't you?
Ooh, is there a story?
Well, okay, so we spent 2 years on this field site, and we had one that we called redfish and one that we called bluefish. And we had, which we're thinking are Zyphactinus and a Pachyrhizotis right now, which are two big toothy fish. And we had different teams split up into excavating them, and we would kind of have little quarrels about which one was better. But if I had to pick, I would have to say the Pachy, the one that was actually in that image earlier, was my favorite one.
Nice.
We have plenty of Zyphactinus stuff everywhere, but Pachyrhizotis stuff isn't that common to find, or at least to pull out of the field.
Cool.
Those are some crazy names, honestly.
You're telling me. You were worried about like pronouncing Actinopterygians earlier. I totally feel that, because there was a lot of, when I was just learning about all these fish names, I'm like, how am I supposed to ever talk about these? Reading them, let alone actually pronouncing them, is going to be a challenge. But
Well, look at you now. You're pronouncing them just fine, I think.
I mean, I'm confident, so
There you go.
that's all that really matters.
Pronounced a different way, we had no idea. Okay, here's a question from Logan, who's 11 years old.
I like it.
They're wondering, what is the oldest fish we have a record of?
The oldest fish or the oldest ray fin fish?
They just say fish, so maybe let's just go with fish, all fish.
Okay, that's a great question. I don't know it off the top of my head. I know the Devonian was the age of the fishes, but I'm not sure if that's really where they started or if that's when they just really diversified and what we're really thinking about as fish.
So what about ray fishes, rayfin fishes?
The earliest ones, I don't know the answer to that. I don't know the first ones. I did at one point, but off the top of my head, so
That's
sorry.
okay.
No worries.
You can't know everything, even as paleontologists. There's just like billions of years worth of stuff to remember. I mean, I have enough hard time trying to remember the names of the time periods as is.
I totally understand that. Yeah, even just learning about the fish that I'm studying, they're in the Cretaceous, but knowing all the fish that are around in the Cretaceous in all the other different seaways, I'm learning them, but I don't know them that well. I don't know much about them in comparison to what I know about these ones. So it's continually teaching me new things.
Any new questions? I have one on I have one in my chat that I have. Sorry, what was that, Brittany?
I said go for it.
Oh, okay. Yeah, so in the Paleo Education watch party, Ian actually has a question for you. Any information about migration patterns in your studies?
Okay, no, actually. But I'm looking specifically at adult or sexually, like the ones that are actually adults in that sense. Like they're not skeletally mature, but they're at least sexually mature. So I'm looking at a very small subset, and I'm not really looking at different stages in their life period. So I don't really have any information about whether or not they've been migrating and how that changes what they've been eating at that time. I'm focusing on like other paleontological studies of trophic structures, pretty much on adults and what they're doing, because in fish, they change how they eat, like their proportions change until they get sexually mature or skeletal, can't say that word, until they're really big. So oftentimes that changes what they're eating, and it really confuses trophic webs and things like that. So we tend to steer away from that, unfortunately. Unless there's some way to look at that soon, it's probably not going to be something that's focused on in paleotrophic studies.
Interesting.
Oh, but with that, I guess I'll add real quick. I did mention there's some medium-sized and some small-sized fish, and there have been different ideas as to why that is, whether or not they start somewhere else when they're smaller and they enter the system when they get larger, or maybe it's sampling bias, but that's possible. I don't really know though for sure.
Well, that looks like all the questions that we have for today, unless anybody wants to throw them in the chat real quickly. Any other
Amber,
questions?
oh, go ahead.
Oh, no. I was literally asking you if you had any additional questions on your end, Gabe.
Yeah, I kind of had a question a little bit, not off topic, but back on the thing about Sternberg. For me and Brittany, we work in mostly like a city area, right?
Right.
For the Sternberg, it's kind of a little bit more in a rural area, you would say?
Yeah. I mean, if you think of Kansas as a state, it's a city. But compared to where you guys are at, yeah, it's a lot more rural. So we are the largest city in probably about a 2-hour radius. And then after that, probably for another like 3.5 hours. So a lot of people do come this way to get things, they get essentials. Well, right now, probably not as much, but generally they do have to go through here, and we're by a major highway. So in that sense, it's a little bit bigger than you'd expect, but it is a pretty small town museum, a small town feel in this city as well.
Like for that kind of stuff, what would you say is its importance to have these small town museums as like a access to natural history for people who have to drive so far away just to get them?
It's so important. Yeah, a lot of different schools, not even just from Hayes, but from all over, have to come here to get that type of experience. And just having something like this that's so accessible and isn't always just impossible to get in a school group into is really useful for a lot of these surrounding communities to actually utilize. And then the things like the outreach programs and the camps really allow for a broader reach to different types of communities, types of students, interests, and things like that.
That's great. I also forgive me for anyone who is in Fort Hayes if I offended you by calling it rural. So I'm sorry now.
Well, get ya.
I'm from LA. I don't know anything else outside of here.
Right. Yes, a lot of my friends that I've met here are from Kansas, and they do consider it a city. So I didn't want to step on any toes, but it is
Out of curiosity,
a city, if you're gonna call it that.
what's the population?
I think it's 20,000.
City. It's a small city, but it's
Yeah.
Oh my god.
Yeah. But that's when.
Are we gonna get into this fight now?
What?
Are we gonna get into this fight now? Just kidding.
Let's see. I have one question that just came up. This is from Maria. She said it may be a little off topic, but she's curious. What kind of fish did baryonyx mostly eat, if you know?
I don't know. I'm sorry. I'm not good at these fish questions, I guess.
Well, fish is a very, very, very broad topic.
There are a lot of fish.
There's a lot.
Absolutely.
All throughout the time periods, there's so many.
Yeah, ichthyology is such an amazing field to study. And I'm sure like trying to look at the food webs nowadays comparative to like what you're looking at, it must just be like something that's not difficult to comprehend, but just like such a cool thing to see the changes and all those trophic conditions and things like that.
Yeah, changes, advancements, like all sorts of different things. So much diversification since what I'm looking at even. So yeah, I can't imagine doing a broad trophic study of fish today. You definitely have to break it up into community structures because it'd be impossible, really.
How did you find yourself in Fort Hays from Minnesota?
Well, that's a good question. It's kind of a long answer, but so that field camp I mentioned earlier that we would do for UMD geology students. While I was there, we had a few professional geologists that would come in and they would talk to us about career paths and what we can do after. And a lot of them would mention to do their jobs, you'd need a master's degree. And at the time, I wasn't really planning on going to grad school ever. I was planning on just finishing and then going straight into the workforce. But when they were talking about that, they were talking about they didn't really care what your master's was in. They didn't care which field of geology. It didn't have to be special to what they worked on, just as long as that you could show that you were passionate about what you were working on and interested and loved being in grad school and can do research. And at that point, I was talking with some of my other friends, and they knew that I always loved the paleo side of our geology classes, if it was in those classes at all. And I was like, maybe I should try to go for my paleontology, like a master's degree in that. And they're like, yes, absolutely. So that really started me to start thinking about grad school. And I took a year off in between undergrad and going to grad school. And during that time, I was really just looking into programs, potential advisors, and I stumbled upon SVP, so the Society of Vertebrate Paleontology, and decided to book a ticket, go check it out, and emailed a couple of potential advisors at that point. And I met up with them there, talked over some ideas that I had for researching if I were to be accepted in those programs. And I really liked my conversation with my current thesis advisor, Dr. Laura Wilson, and how she ran her lab. So that's how I settled on coming to Fort Hays. I really liked Laura. I really liked the opportunity to work on Cretaceous age specimens. So that's how I ended up here.
Awesome.
Here's a good question from David again.
Yeah.
What's the most underrated fish in your opinion, fossil or modern?
Oh.
Underrated.
Yeah, underrated. What does that mean? Oh, there's so many crazy cool ones. And I don't know them all. So one that I think is really cool is the paddlefish, which is a filter feeder too. So you know how I mentioned how we don't have those really big ones anymore for filter feeders in a system? We don't, but we do have some. And one of them is a paddlefish, and it's kind of medium size and it's usually freshwater. But it's cool that they didn't completely go away, that bony fish still have a foot in the door for that type of energy consumption.
I love paddlefish. I saw them for the first time when I visited the what is it? The Shed Aquarium in Chicago.
I went there too.
It was so cool because like they just swim around with their mouth open and like they're just going back and forth. It was just looked like they were screaming too the whole time. So we just kept recording them.
They're so cool.
I have one more random question.
Okay.
Do you think how do you say it? Xiphonactis?
Xiphactinus.
Do you think they would have liked Krabby Patties?
Ooh. They're grumpy looking. They're called the bulldog fish for a reason, so I feel like they wouldn't enjoy happy things like that.
They're called bulldog fish?
Yeah, sometimes people say they have like a bulldog face just because they have the upturned jaw and the big teeth, but they look grumpy.
Yeah, that's true.
But maybe that would make them happy. So
that's true.
Jury's still out.
Squidward end up liking like Krabby Patties, so maybe they can get them to join.
Sure did. A little too much.
I'm just saying.
You know what? You're right. I think that they would have thoroughly enjoyed a Krabby Patty.
Never say we don't fit to a theme here. Awesome. Well, that looks like all the questions that we've had for today. So thank you, Amber, for joining us. This was informative not only for us, but I think for everybody who was watching today.
Thank you so much for inviting me, guys. This has been really fun.
Of course.
It was really cool. I learned a lot about fish.
Good.
All right, everybody. So next week we'll have 2 more Fossil Friday web chats, one with Michael Zeigler, who is going to actually maybe, hopefully, possibly show us his field site and take us outdoors for the next one. And then we also will be joined by PBS Eons hosts, Kelly and Blake. And so they're going to join us next week to talk about PBS Eons. If you've ever seen that show, it's a great informative science communication platform from PBS. And so we would love to see you next week, and we will have a great day.
Bye, everybody. Thanks, Amber.
Thank you.